if I go in too far. I'm not going to go into anything, but if it seems that way, just ask me to repeat something or ask a question. Okay, so the data science process, what we're going to talk about mainly is, and again, I want you guys to get a good intuition because all you guys can do this. All you guys can do this. First of all, let me say also before I start this, I think it's important, you guys, there's not enough talent to fill all the positions that are available, you guys. Let me ask you guys, most of you aren't in data, but how many of you are aspiring to be in data? About 5 of you? The rest are just kind of fans or something? Okay. But I encourage you guys. I mean, I can't think of a company, if not now, very soon, where data will be a big part of what they do. There's just not enough talent for data jobs. So it's a great time to be doing what you're doing. Okay, so we're going to talk about what question you want to answer. It's very important that you think about because you're asking your data a question. And it's got to be in a certain form, so we're going to talk about that a little bit. Obviously, you want to get the data, and there's different ways that you can get your data. We're going to talk about exploring the data, looking at your data, cleaning the data, and you do all of that before you even get to modeling the data, which is the machine learning part. Okay, so we're going to talk about those things. So what question do you want to answer? First of all, the question has to be answerable. I'm going to give you some examples of that, and the question should be very specific. And I can't tell you how important it is when I say specific. Let's say you have some data. Okay, we'll talk about how to get data. It's important if you guys can get some data and play around with it so you get used to what data's like, how to manipulate it. So let's say we have some data. Research shows that there's a U.S. pay gap between men and women, right? There's, women make about 82 cents for every dollar that a man makes, United States. Okay, there's different reasons for that. I'm going to clarify that. It's important that you understand your data because on the surface it may look one way, but it may be totally different. And you, as a data scientist or data analyst, need to understand that's why you're being paid. That's the value you're going to add to a company by having some insight in data. So when you look at men, white men specifically, Asian women make about 94 cents, white women 82, black 68, and Hispanic 61 cents. And there's different reasons for that. Women dominate certain professions that aren't high paying, such as childcare professions, cleaning. Women dominate probably 6% of the minimum wage job. There's a lot of reasons for that, but I want to clarify that a little bit. When women are on the high, these are the top 10 highest paying jobs in the United States for women. Women, less than 3% of women are in these jobs, but women who are in these jobs, there's parity for the most part in these positions. And as women, and in fact, there's a bias for women in STEM positions. Much more. Women and minorities, there's a bias for them in certain STEM jobs and these highest paid positions. So in these jobs, there's parity for the most part. Okay? But when people in their 20s, there tends to be parity between men and women, although women, when they first leave college, tend to take a more paying job than a male's first job. Women's majors tend to be a little bit less paying than men for different reasons. For example, you'll have women who may teach, but they tend to teach in elementary school or lower, where there are more men who teach in universities. There's different reasons for all of that. But the main thing I want you to see, as people get older, the gap gets wider. And there's reasons for that as you look at your data. You can see it's 6%, 8%, 23, 34, and 35 as women get older. Okay? And the biggest reason for that is that women are penalized for childcare. Women more than men, 40% of women either significantly reduce their work hours or actually leave the job force in order to take care of a child or a family member. Only 25% of men do that. Okay? The other thing is when a couple has a child, women on average take 12 weeks off. Men on average take 1 week off when they have a child. And so what that ends up doing, women, when they do enter the workforce, they've lost some time, they've lost some experience. Sometimes they're away from the workforce for a significant period of time. So all those things enter into a lot of the pay gap. But as I said, STEM positions are somewhat biased toward women. So, and then last thing here, women with no children make a little bit more than women with children, and men with children make a little bit more than men without children. So let me ask you guys a couple of questions. As you look at data like that, the reason I got into that, one, I want you to think in terms of data and how data is, and exactly looking at your data and understanding your data, because again, you'll be paid for your domain knowledge. The question you can ask, and most of the time a company doesn't know the question, they just have data, and they need someone to figure it out because either you have domain knowledge or you have some insight or you're good with the tools to figure out what's going on with data. So with this, one question that you probably wouldn't want to ask is, for example, will women ever be paid more than men? Those are some questions, a lot of people think of generic questions like that. Those questions, one, not answerable, for one. And for two, as I said, you want a very specific question for your problem. Okay, I don't know if any of you remember Magic 8 Ball. Anyone know what a Magic 8 Ball is? Where you shake it, and does she like me, or whatever, right? That's what this is like. It asks a very specific question. So the question that you may ask might be, will this, let's say we'll take a woman, will this woman make more than the median salary for this position? Or will this guy make more than the median salary, or will this guy make more than that guy? Or whatever, so your question would be for a given position. So your question would be very specific when you're looking at your data. Okay, and again, I'll give you some examples in just a second regarding that. Next thing is getting your data. I'm going to take my time here because I put a lot up here because I think it's so important to play with data, you guys, and to get with data. First thing, these are some open data sets. First thing is Kaggle. Many of you may know Kaggle. It's kind of a competition site. And Kaggle has some great data sets, great competitions that you can get involved in to learn how to do some machine learning. Another one is Amazon's web services site. They have some data that you can get. And most of these are, when you look at companies, kind of slanted toward their problems. Data.gov is government data, anything that you might have that's publicly available government data. UCI is a very popular site. UC Irvine's, it's from UC Irvine. They have a lot of, in fact, the IRIS data set that we're going to talk about in a little bit is where that IRIS data set is. Some of you may have heard of 538. They do a lot of great data visualizations, political data, political things, sports things. But it's worth going there. 538.com is a great website. Quandl has a lot of financial data. A lot of people are interested in trying to predict the market. So Quandl's a great place for that. And of course APIs, Twitter, Facebook, Spotify, all those people have APIs to get access to the data. A lot of people do maybe sentiment analysis on Twitter and different things like that. A lot of companies will do that. And of course your company's data. And finally, I want to highlight these because Google just about a month ago came out with this. That's how important data is. Okay, Google has a specific area just for data sets. Came out about a month ago. ProPublica, a lot of magazines and journals, magazines and newspapers will use this. And ProPublica is a great source of data, and it's a lot of trending data, for lack of a better term, very popular data right now, such as maybe recounts on the elections that just went on and things like that, but a lot of publications will use ProPublica. NASA is good for anything having to do with space or Earth. A lot of good things if you're interested in anything like that. Some people were asking about farming in a previous batch. We got a lot of good data from there. And the World Bank is outstanding because it's not just the U.S. It's not just U.S. It has world data. So if you're interested in other countries, data from other countries, then World Bank. Any questions on any of that? Quickly, some of the challenges as you guys look at data. One is insufficient quantity of data. The number one thing you guys can do is to get data. The best thing that you can do. An outstanding algorithm with less data than an average algorithm, that average algorithm will do better with more data. Data is the most important thing. A lot of times the data may not exist, and sometimes I've had to go out and create my own data. We have to go out and collect data for maybe a specific question that you're asking or something that you want to gather. Non-representative data. Maybe the data was collected and the research was on women and you're trying to apply it to men. That can be a problem. Poor quality of data. A lot of things are missing. Instead of saying maybe if a feature was missing or the value was missing, someone might put a 0, and that's never good to put a 0. It should just be left blank. Or an asterisk, or things that a machine can't read. Okay, then finally, irrelevant features. Maybe have a data set, but the features aren't related to your problem. Okay, you might have the person's name, person's address, personal security number. None of that is useful. Almost never, ever is any of that information useful. And you'll see why in just a second.
Question.
Yes?
So how good is this data described as to what it is? Like you could have like gazillion columns of data, how good it is in description from all these sites.
How good is the data?
Yeah, that means, is it well described that you can understand, or you have to dig deeper?
Almost, well, and Kaggle, almost all of Kaggle's data sets and certain sites are almost always clean.
Okay.
Because it's a competition site. They don't want you to worry about cleaning it, so it's clean. It's up to you to develop a model to predict something. But in general, you're almost always going to have to dig into your data and understand it. Almost always. I mean, the real world, your data is never good, never clean. You know, so you're almost always going to have to do it. But I'll give you some examples of that. Okay. Anyone here of Paranoia? Anyone know that term? Nobody? I think of Paranoia in terms because when we're doing this data science project, the point is these algorithms are frantically trying to find some pattern in data. And I think of that, in my mind, I think of Paranoia because as humans, that's what we do. We try to find patterns in data. We just babies do that from birth. They identify faces. And we do the same thing. We see something, we make some pattern out of it. It's just common. Anyway, it has a term, it's called paranoia, where we see something, we try to identify it. And to me, that's what I think of when I think of machine learning. It's frantically trying to make some sense. It's trying to see something we can't see. Too many features, too many dimensions, trying to find some pattern that makes sense to it. It may not be the pattern that we want, but it's frantically trying to find a pattern. Okay? So let's talk about exploring the data. You mentioned about the data. So most students, the average student leaves school with $27,000 in student loans. So let's look at this. Let's say we have this data, and we want to predict who's going to default on their student loan. Maybe we can help them. Maybe we can do some things a little bit differently for them. Offer them ways to refinance or something. So that's going to be in the interest of our company to help them. So we get this data, and your job is to identify, is to predict who might default. So the first thing you want to do when you get data, now that you guys have all of these sources of data. Oh, one other thing let me mention. If you have a specific problem, Google open source and then whatever that noun is, or verb, whatever you're trying to search. Open source, I mean, not open source, open data, that's what it's called, okay? Because these are called open data sets that are publicly available, that aren't proprietary. Just say open data and then horses, or whatever you're interested in. So you don't have to limit yourself to these to the sites I showed you. Anyway, the first thing you want to do, when I get a data set, the first thing I do is look at it, make sure I understand each feature. And if, again, as data scientists and machine learning people, columns are called features in machine learning. Okay? So make sure you understand each feature, what it means, because these are straightforward, but some will be in code. Some will have L-2, you don't have a clue what that means. Make sure you understand what each one of those features is. Okay? Second thing I'll do is I'll do a summary of the data. And all this you guys will see at the end, how this is all done in Pandas. So the first thing I'll do is do a summary of the data, because one, see that first row up there, all those numbers should be the same. And if they're not the same, you know you have some missing values. You have to do something about that. This is the first thing I'll do. I'll do a summary of the data. I'll look at that first row right there, and if those numbers aren't the same, I know I have some missing values that I'm going to have to replace and compute. I'm going to have to do something to that. Another thing, again, kind of a sanity check, you're looking at it, look at age. And you guys see that minimum number? Does that make sense? Why?
Student loan.
You're not going to be 2 and have a student loan, right? So that tells me when I look at my minimum max values, let's see if that, I'll look at the mean. Does the mean make sense? So that gives me just a general summary of my data so I know what I'm working with. Are values missing? Does it make sense when I look at it? Is it in normal, in range? Now, if I don't have domain knowledge, I may not totally understand what the data should look like, but if I do, which I have some sense, that looks reasonable to me, okay? Next, I'll visualize my data. This is called a pair plot. You always have to do a pair plot. On the diagonal are histograms, or the frequency counts of certain features. This is just generic. But what a pair plot does, it goes pairwise. It compares every feature pairwise and look at correlations. So you can see what features are related to each other and what features are maybe related to the target value. And that's another term. Columns are features, what we're trying to predict. And as you said, in supervised learning, what we're trying to predict is called the target. Okay? So the problem is what's called collinearity. We don't want a lot of features that are highly correlated. That's not good for machine learning algorithms. If you have a lot of features, let's say you have 2 features like height and weight that are highly correlated, you should either drop one or combine them, like in BMI, into one feature. But you don't want to have a lot of features that are highly correlated. So the pair plot allows me to look at that.
In what way are you seeing when you're ready? Or is there?
Well, this is a little bit different because I have it separated by, this is the iris data, and we're going to get into that a little bit later. But see how many of these are, this one right here, those are hard. This feature, which is, this is just mock. But this one, these two features right here, whatever that name would, there would be a name, I'll give you an example later, there would be a name here. Those features are highly correlated. You see how there's a linear relationship? They're highly correlated, where these aren't. You know, there's some relationship, but if they're highly correlated, and what you can also do is print a matrix that also shows the actual correlation number. If it's greater, say, than 0.8 or something, they're highly correlated. Good question. And next, let's talk about cleaning the data. Now, you guys pay attention to this. Like I said, you guys, this isn't, you guys can do this. I think that's so important for me to convince you guys of that, how important these things are. So I want, when you leave today, I hope you guys get a good intuition. You may not know the tools, but you have a good intuition. If I had a data project that I'm working on, right now we're talking about traditional machine learning, I have a good sense of how I would guide that project through. I may not know how to use, maybe you don't know Python yet, maybe you don't know some of the libraries, Panda, scikit-learn, some of those things that we'll talk about. But I want you to get a good intuition. If I were to sit down, I have this question in my head, you know, hope you have a good sense of how I would go about it. Okay, so first thing we do when we do this, we're going to clean the data. First thing you want to get rid of is anything that's unique. There's no pattern in unique data. So you see loan ID, social security numbers, driver's license numbers, those are unique things, they're useless. They're not going to give you any pattern, so you want to get rid of it. Okay, name is the same thing. Names are relatively unique, not absolutely unique, but in general they're unique. And the problem with that, again, like I said, Paranoia, your algorithms are frantically trying to serve you and find some pattern in this data. And almost all good data that's clean and organized, there's going to be some pattern, some ability to predict. You might have to do some things like feature engineering, some other things that we're going to talk about. And the problem with this algorithm might say, you see the two people that who have defaulted right here? This algorithm might say, you know what, I got it. If you have a U in the middle of your name, that's the pattern. Or if you have 6 letters, that's the pattern. So names are no good, get rid of that. It's going to try to find a pattern if it's there. It may falsely find a pattern. If you have 6 names, it's going to predict that you'll default. So anything that's unique, get rid of it. Okay? The next thing, machine learning algorithms almost without exception. I'm not going to get too much into the individual algorithms, but decision tree, if you guys have heard of decision tree or random forest, they don't necessarily have to have numbers, but almost every other algorithm wants a number. So this yes and no, how would you guys convert that? Yeah, binary, right? Whoops. Oh, you know what? Before I do that, let me show you one other, because we're still playing, so I'm going to come back to that. Look under loan balance. This is a common mistake that people make. See that comma? Can't be any commas. That's a string. So I have to get rid of that comma. You guys see that? Right there. That's a common mistake that people will make. Okay, so that has to be removed. See where it says next payment, where there's a missing value? Some people put a 0. You can't put a 0 because it looks like the next payment is 0. But a lot of people with a missing value put a 0. They'll put an asterisk, they'll put a dash, they'll put all kinds of things. That's something you're going to have to deal with. You have to do something with that. You can either, in Python, it's called not a number, and so it will be ignored. Or you can what's called impute it. That means you're going to have to come up with some reasonable value, which in this case might be, I'll put the mean number in there. You have to have some reason for it, but there's or you can drop the row. If you have a lot of data, just drop it. If you don't have a lot of that. Okay? Now we're transforming the data. So as you guys see, we're going to train that first with a binary. It'll be lead numbers. Okay? Now here's the one thing I that's hope that you guys can kind of see. When you look at loan type, when you go through each of these features, numerical features, if it doesn't make sense to average them, then you have to do what's one-hot encoding. And I'll illustrate here. See loan type? Let's say one loan type is a university loan, another one is a private loan, another is a government loan. Is the average of a school loan and a government loan or private loan? No, it doesn't make sense, right? So it doesn't make sense to average that. It's categorical, they're arbitrary. They could have been called 100, 200, 300. Or A, B, and C, or yellow, green, and blue. They could have been called anything. So when that happens, you have to do what's called one-hot encoding, where you break them all out into their own feature. So you're adding features. So now it's loan 1, loan 2, and loan 3. And only lone one, that's why it's called one hot. Only one can be hot. So lone one, if you're in lone one, you have a 1, everything else is 0. If you're lone 3, you have a 1, everything else is 0. That's called one hot encoding. Okay, so if you have more than 2 items, you can do binary if we're just 2, but if it's more than that, it's categorical, you have to do what's called one hot encoding. Again, we're getting our data in shape so we can do our machine learning. Okay, does it make sense to get an average loan balance? Yes, yeah, don't be shy. Does it make sense to have an average next payment? Does it make sense to have average months delinquent? So we're good, those don't need to be touched. Okay, what do we have to do for defaulting? Yeah, we have to have numbers there. So now we have all numbers. So we look pretty good there. We had to do some binary transformation. We did one hot encoding, the other ones were okay. Okay? Now, DataFrame. I want you guys to understand. Who's heard of the term DataFrame? I know you should, but anyone else? No one. Okay, one blind mission. DataFrame is usually what we're looking at. It's what we like to see. When you're in Pandas or anything else, it's just a table that you might be used to in Excel. That's a data frame. It's for us, not for the machine. When you're finished using your data frame and clean your data, it's going to come out of that data frame just as numbers, and I'll show you in just a second. So here's your data frame right here. These are called features. So when we talk about features, we're just talking about whatever columns or whatever additional things that come with the data that describe the data in some way. Okay? It could be, as we said earlier, it could be how much someone makes, could be their gender, could be the type of position they're in, or the employer, all those could be features. Okay? Now notice something, where we have features, it's a big X. That comes from math. If it's a matrix, because it's more than one column, it's a large X. Okay, so features you'll almost always see in X, in a capital X. Okay? That's the target. And what's the target? Who can tell me what the target is? What does the target mean? It's what we're trying to predict. Right? It's what you want to, when you get new data, when you get a new student who's leaving school, so you don't know what happened to their loan, you have to predict whether they're going to default or not. Okay? And you're going to learn that from the target. Okay. And then that's a sample. Just one row is a sample. That's just one student. Okay. Now let me point out one other thing to you guys, because I want to talk about standardizing the data. Some of you might have heard the term standardizing and normalizing, and I want to clarify why that's important. You see where loan balance is in the thousands? See that? And next payment is in the hundreds? And then months is in the tens or ones? See that? They're on totally different scales. And when you're using an algorithm that looks at distance or things like that, larger numbers are going to dominate. And it doesn't mean that loan balance is a more important feature than the other one, but it's going to look like that to some degree. So we have to do what's standardizing, and I'll explain what that is. And the gist of it is you want to get everything on the same scale so you're comparing apples to apples, and I'll show you how we do that. Okay. First thing, when we standardize, we're looking at the spread of data. For example, if you look at age in the population, it's probably going to be like the green line there. Greenish yellow one there, I guess. It's going to be kind of like that, very spread out, right? But if you look at age for female gymnasts or models, it's going to be very narrow, like the blue line. So that's important to note when you're looking at, when you're standardizing your data, okay? That measures the variance in the data. How much does that data vary? Okay, so stay with me now if you haven't had a lot of statistics, because this is why we standardize our data. The way we standardize our data, first of all, you get a feature. There's just one column. We get the mean of that column. And then we say, how much does each value vary from the mean? So if you look at that third column right there, we square the deviations from the mean. Okay? It's not important that you memorize this, but again, I want you to get intuition while we do certain things. So these are the features in the column. Those are all the different values for whatever feature that is. Right? That's how far those are from the mean at the bottom, which is 4. So that's the deviation from the mean. That's the squared deviation from the mean. So the variance, go ahead.
Why do we square them?
Well, if we didn't square them, it's an excellent question. Why do we square them? Let me give you an example. Let's say the mean were 4, right? And we had one value that was 3 and one value that was 5. They would cancel each other out. Because one would be one above, one would be one below. And if you add those together, we'd say there's no difference. There's 0 variance. So by squaring them, we can sum and see what the deviations from the mean are. You guys see what this question is? Why do we square them?
Why can't you cube? No, why only square? Why can't you cube?
You can maybe take an absolute value or something, I suppose. It's just similar. I didn't invent this, but that's what variance is. But the reasoning though is that if you don't square it, they would cancel out. Okay? So anyway, square deviation from the mean. And you divide it, this is statistics, it's n minus 1. That's why it's 9 instead of 10. Don't worry about that. It has a difference between the population and the sample. Don't worry about that. So that number comes to 6. Standard deviation is the square root of the variance. Okay? The standard deviation is the square root of the variance. And the point is that says, the reason that's, I know this probably was convoluted, and what in the world does any of this mean? But the reason this is important is because of this. For the normal distribution, okay, we know that 68% of the data is within 1 standard deviation of the mean. So now, when we standardize our data, and that data is no longer going to say 35,000 and whatever for a loan, it's going to say maybe 1.5, which means it's 1.5 standard deviations from the mean, which we know, well, let me make it simpler. Let's say it's 1. We know that 68% of the data is within 1 standard deviation of the mean, so it's a relatively normal value. If it were 2, 95% of the data is within 2 standard deviations of the mean. So we know if it's 2 standard deviations from the mean, it's a little bit more exceptional. 3 standard deviations from the mean is rare, but that happens. So that's now we can look at, I don't care what it is. I don't care if it's in terms of dollars, or in terms of pesos, or in terms of whatever it might be. We're going to standardize it. So now, only thing I need to know is how similar are you to the center of your data? How close are you to your mean? So that's all you're looking at when you standardize the data. And so those numbers, let me ask you guys, let me extend out. 68% of the data is within 1 standard deviation of the mean. 95% of the data is within 2 standard deviations of the mean. 99.7% of the data is within 3 standard deviations of the mean. Because you will find some people who are approaching 8 feet tall. So they'd be a little bit beyond 3 standard deviations of the mean, but it's rare. Okay, so let me ask you guys this. When we standardize our data, those numbers should fall between what and what? Excellent. He's paying attention. Plus or minus 3. Do you see why it's plus or minus 3? Because every value is going to be within plus or minus 3 standard deviations from its mean. Now we have everything on the same scale. Okay, so if we have Jeff Bezos, we know he's going to probably be at 3 point something in terms of salary. He's going to be way out there. So we know, so I don't have to know what he makes. I just look at that 3 and say, wow, that's an acceptable value. That's all I need to know. And then if I look at someone's height, I don't have to know how tall they are. I just know, wow, that's an acceptable value. If it's negative, it's below the mean. If it's positive, it's above the mean. So standardization allows us to compare apples to apples, and machine learning algorithms like that, especially when they look at distance for measure.
So in this case, do you remove anything above 3 and below -3?
Do you do what?
Do you remove the data from your data set?
Do you remove it?
Yeah, I mean, if it doesn't fall in that...
You know, that's a good point. Again, that's a domain knowledge thing. If that makes sense to you, where it's an outlier, you can say that. You can say anything above 3, 2.8, I'm going to drop. That's a domain knowledge. It depends. You know, again, if height is important and you're looking for certain things, no, I wouldn't. But if that's so rare, then you can just say, I'm going to drop those. That's a good point. Excellent. Yeah, you can use that for that reason. We'll talk about some other things when I talk about a box plot. Yeah.
So this assumes it's a standard deviation or a normal distribution.
Yes. And in general, depending on what you're doing, but if you have a large number of data, it's going to approach that. If you have a lot of data. Yeah.
So this is...
Yes.
You're doing this for one of the features, right?
It's just one feature.
One feature.
Well, all features, but the mean and the standardization is based on one feature. But each feature will have this done to it.
So if it's skewed towards either side,
Yes.
what do we do with that?
Well, that's a good point. If it's skewed, well, it depends what you're trying to do. You can still standardize it, but remember earlier how we said imputation, we're going to try to replace some data and it's skewed. You probably wouldn't use a mean, you'd probably use a median. I don't want to get, that's kind of a statistical thing, but that's a good point if your data is skewed. But in general, the issue, a lot of times I'm talking about having a lot of data. Usually if you have a lot of data, it tends to approach being normalcy. If you have a lot of data. If you don't have a lot of data, you have all kinds of problems. If you have 50 data, you know, it could be anything. It could all be taught just randomly.
I'm assuming that there are tools to do this, right?
Yes.
Okay.
Yes, oh, for sure.
Okay.
Good question. There's tools to do, yeah. Again, this is for intuition, but the libraries will do this automatically for you. But at least I want you to understand why you're doing it and the significance of it. Yes?
Do we have to make every data set fall under this normal distribution curve?
Say a word louder.
Do we have to make every data set that we get to fall under this normal distribution curve? Because every data set.
Not necessarily. Well, you know, the simple question is, it'd be easier to do it. Not all algorithms apply it. I can tell you neural networks, it's very important for neural networks, but not all algorithms will respond necessarily to it. But in general, it's a good habit to do. But if you don't know some data sets, it may not make a difference. And as I said before, decision trees, things like that, doesn't matter as much. They can even take strings. Okay, and I'm not getting to the different algorithms, but in general, it's a good habit to do that. Okay, there's also a term called normalization. I won't get too much in that, but usually it's standardization, which is what I just showed you. Okay.
So if it doesn't fall into like when we get the data set as part of the cleanup, we do this, we try to make this, we try to find this.
Once you're finished cleaning, notice the order that I'm doing things. Once you're finished.
Data doesn't fall into that. Like let's say I have a data set. The first step I do is I'll find some features, and then like I'll do the first step of standardization and find to make that feature fall into the standard.
I would do this last.
You will do this as last.
If you do it first, you're getting the mean from early on. You might be dropping things and changing things and dropping rows and imputing, and that mean's going to change. I would do this once you're finished doing all your transforming and cleaning. Now is when you want to standardize.
But I thought that's the step that you're doing right now. You're taking a feature, like let's say the load balance,
Right.
which was like 5-digit number, and then you're trying to find out the second step you're doing is this, right? That's what you're doing.
No. The first thing I did was to remember we visualize the data, then we clean the data,
Yes.
then we transform the data. Once I'm done with that,
Correct. And
then I do this.
Yeah. Now my question is, while you're doing this for a particular feature, if that feature doesn't fall into this graph of normal distribution, because there could be features that can fall outside of, there are a lot of curves out there, right? Normal distribution is one of them. If it doesn't fall, that feature doesn't fall into this, what should we do?
Yeah, that was my question.
Very good question. He's saying, the question he's saying, if you guys can hear him, he's saying if it doesn't follow a normal distribution like this, okay, what should you do? Two different things that I would do. Again, the reason I hesitate to answer is a lot of this comes down to domain knowledge. It depends the significance for your problem, what your data problem is. In general, what I would do, I'd do it initially without it and see how it performs, and I'd do it with it and see how it performs. But more than any of that, I'd get more data. That'd be the number one thing I do, I try to get more data. You can't always do that, but that solves so many things if you get more data.
It's probably nothing called normal, right? I mean, it's
No, it approaches normal, yeah, rarely. I mean, there's certain things in height and things, age, there's certain things in the population that are normal, but on most data problems, unless you have a lot of data, it tends not to be, you're right. That's why it's important to get, the amount of data is very important. Okay, so just visually so you can see it, in statistics, it's called a z-score. Okay, we're calling it standardization, but in statistics, we hear a z-score. Anytime that you take a standardized test, notice the word standardized, ACT, GRE, SAT, you'll get a z-score, which is how far are you from the mean of everyone who's taken this test, and you'll get your percentile. What percentile did you score? Okay, so z-score is what is called in statistics, and the way that's done, and it's easy to do in code, but again, it's done in the libraries, is X, which is, notice that it's a small x. You gotta know the difference. What's the difference between a big X and a small x?
Big X is the feature.
Big X is all of it, all of it. Small x is a specific data point. Remember, big X was that whole matrix of all the features and all the rows. 1x just give me one row. Give me one item. So X means just me. Me, my height, age, salary, whatever it is. I'm looking at me minus the mean of that whole column. Right? So subtract me from the mean. So how far am I from the mean? And then divide it by the standard deviation. It says how many standard deviations I am from the mean. Okay? Don't have to memorize any of that. I just wanted to say it. Okay? So at least you've seen it. Okay? So I'm not going to change it. Let's leave it the way it is. You're not going to say this is how it was originally. So I didn't standardize this. Okay? So this is a data frame. That's what machine learning wants. So this is for you to visualize, to manipulate, to get means, to drop rows. Once you're finished, this is what machine learning wants. It doesn't care about any of that. And so,
You just drop the header and drop the labels?
well, you'll see, yeah, what it's called, it's a calling pandas, and I'll show you guys a little bit later in the library. But the point is, this is what you want. You're going to put the features in X, you're going to put the target in Y. Okay? And that's what goes into your machine learning algorithm. It's going to say, given X, predict Y. And it can do that because I have these X's. I know I'm learning from this data because I know what happened to these X's. I know what their target was. Now when you give me some new X's, I have to learn from that data and accurately predict what's going to happen.
So if I want to predict 2, then it's just 2 separate problems?
Want to predict
If
2?
I want to predict 2 different targets. Like in this case, default, but I mean, maybe something else I want to predict, then it's...
Well, you'll always have one target. You have more values than one, but your target, you only have one target. The target can be more than one number, though. For example, if you're trying to predict, like I'm going to show you guys, for example, a problem of digit recognition. You have 0 through 9 for handwritten digits, right? So you could have 10 things at the end for the target, and hopefully the highest probability is under the number that it is. But yeah, you wouldn't have 2 different predictions. Yeah, these are good questions, though. Okay, next, we've done all that. Okay, let me go back. We've gotten our data. We've looked to see, do I understand, does it make sense? Then we've visualized our data. Then we cleaned our data. Then we transformed the data. Then perhaps we standardized the data. Now, we're ready. Then we took our data and we put just the numbers into X for the features, and we put just the target as numbers into Y. Now we're going to do what's called a test train split. Okay? What that means, we take our whole data set, all the data that we have, what's 150 or 10,000 or 10 million, whatever it is, we take our whole data set, and what's typical, and you can change this number, what's typical is to have 70% of the data put in a training set, and 30% of the data putting into a test set. Okay. Anyone know why we split the data? I know you do. Go ahead, you can answer.
Preventing overfitting, so you don't learn your data set.
That's part of it.
And also because you need to, so it doesn't make much sense to test on the same data that you're training with.
Yes.
Because it doesn't give you any new information.
Yes. So the term, he's right, but the term is so that it can generalize. I get it with this data, but now what about when I get these new customers? How can I predict what they will buy, what they will click on? Can I predict who will win what the stock market will do tomorrow? Whatever it is, so I want to be able to take this model that's learned from this data, and hopefully it will generalize to unseen data. And so the reason we train on our training set, and what we do is we get rid of that test set. We don't look at it, we don't touch it, you can't do anything. You can't test your test set and then go back and change your model a little bit because it's going to seep into that. It's not going to generalize. You're going to as he said, you're going to overfit. You're going to learn your data so well. You're going to get 98% accuracy on your data and 53% when you come to new data.
2 questions. One, is 70-30 just a general guideline?
Yeah, it depends. Again, if you have a lot of data, you can do all kinds of things. You want to go 90-10. If you have little data, it depends on how much data you
always
have.
have something 50 and above, or 60 and above, or 70 and above in the training?
Well, again, it's more complex than that because it depends on the algorithm.
What is the drawback in maybe having a 50-50?
Anyone can think what the drawback in having 50-50?
Might not have enough data.
Man, you're good. Data. You're training on less data. The more data, the better your model's going to be.
So then why not go higher?
Because your test set will be too small.
Okay.
See, it's a balance. So it depends on how much data you have. Those are great questions. Seriously, those are good things that anyone should think about. Because again, those are things that you're going to have to figure out. There's no 70-30 is the default in most libraries. But you may have a gigantic data set and go 95-5 or something. It's up to you. Yeah.
Is this parameters you should take into account, or is this just?
Say it one more time.
Is this parameters when you're doing this that you should take into account, or is it just something that, okay, let's just start with this?
I'm not sure.
Like the amount, the ratio between the training.
Between 70 and 30?
Yeah.
Well, again, not knowing much about your data, that's standard. Would be just a 70-30 split. And again, depending on how much data you have, depending on what your problem is, depending on how many features, there's so many other things that can come into play, but in general, 70-30 is the traditional split.
Is it randomized, I'm assuming? I mean, you just randomly split?
Those are great questions, yes.
And then once you randomize...
I'll show you when we get there, because these are great questions, all this is in the library, but the point is, it's good that you're thinking that way. The library does allow that for you, because many people have done this, and so they know these things, but those are great questions that you're thinking that way.
Once you split, then you go back to the previous step we did there, the median, I mean, do you still...
If you put a seed, I'll show you when we get there. Those are good questions. He's saying when you randomize, you're going to get the same, and we'll get to that. So anyway, so we got rid of our test set. Remember, we don't look at that test set till we're done. When we feel good about our model, right? We have a model that performs well on our training set, and we feel good about it. Now we're going to step over to our test set and hope that it generalizes well. But we don't play around with our test set. No, I didn't do that well, and come play around and go back to the test set. We don't touch it. It's gone. It's out of mind. Okay, so we have our training set. This is our training set, which is only about 70% of the data, whatever split you chose. So the learning process is, we get our training data, we apply it in some way with a machine learning algorithm to that data. There's different algorithms, okay? Comes out assuming it's classification, not regression, but assuming it's a class, it comes up with a classifier. So that's the model. The model says, I get it. I got the pattern in this data. I got it. You give me new data, I'm going to give you prediction. That's the classifier. Now, hopefully any new data you get, unseen data, new data, hopefully the prediction will be accurate. You can measure that when you do your test set. That's why you do the test set, so you can say, how did this thing generalize on unseen data? It didn't train on that test set, it doesn't know any of that data. Okay? So that's kind of the pipeline, so to speak, in terms of the learning process. Let's talk about model selection. I'm not going to talk about these algorithms, but these are some of the most common machine learning algorithms. And one of the biggest questions people will ask is, which algorithm do I choose? How in the world do I know which algorithm to choose? First of all, let's take linear regression off. It's a little bit different. It's not a classifier. It will give you a continuous output. You know, predicting tomorrow's weather, predicting a stock price, predicting anything that's going to be a continuous output, not a class. Okay? All the other ones are classification. So the answer to that is there is no best algorithm. What you typically would do is pick one from each family of algorithms, because they all are different. I'm not going to talk about them right now. We talk about that in the class, but right now I'm not going to get into this, but the point is that you'll take each, maybe something from each algorithm, and I'll show you how we proceed. First thing you do, let's say we picked logistic regression. Yes?
So this data set of this problem is actually a regression problem, right? Because we're trying to predict the value. At the end of the day, we're coming with a model, y is equal to x, right? So it's
Trying to predict, we're trying to for
predict
which problem?
the person will be for the pseudo node, right? That's the target.
But I'm sorry, say it one more time?
So this is a regression problem or not? Like,
There's no problem. I don't have I'm not talking about any specific problem. Let's just say this.
on the pseudo node, you're not going to
Well, we can stay with that if that's better for you, but that's not a regression problem. That's a classification problem. We're trying to say, will they default or will they not default? That's a classification problem. But I wasn't talking about any particular data set, but if it's better, let's leave that in our heads. Let's talk about that. Yeah. Okay, so let's say I'm referring to that. So we're all speaking the same language. So let's say we're looking at that and we choose logistic regression. The way we test our training set, or way we train, is what's called K-fold cross-validation, and 10 is the most common fold. We have 10 folds, 10-fold cross-validation. And what we do is we take our training set, which is 70% of the data, we break it up into 10 different folds. Okay? So 10% of whatever that is. Okay? So each fold is 10% of the data. So we have 10 folds of the training set. Okay? We take 9 of those folds, train on those folds, and then we take the fold that we didn't train on, it's called the validation set. We train on that one right there, and we're going to get a prediction on how well it did. You guys follow me? So we take 9 folds, we're going to train, we're going to try to learn whatever patterns we can there, and then we have that one fold we didn't use. And we're going to say, how did it do on this one fold? Okay?
So within the training set, you are splitting again into 10 different
Yes. Yes, the library, you don't have to do it, but yeah, you'll just say train test split, you'll get it, it'll be split like this, yes. Okay. I mean, in the cross-validation, yeah, we do cross-validation. So you'll get one score, maybe you did 74% accuracy, 93, 47, whatever it is, okay? Then we'll do that again. 9 different folds, hold a different one out. Okay?
This is you're explaining logistic regression algorithm.
No.
This is in general.
This is a logistic regression. It could be any algorithm. I'm
Okay.
explaining how we would validate. Let me go back up. I want to make sure you guys stay with me because this is important. Most people say, which algorithm do I choose? And I'm showing you how you can determine which algorithm is best with your data.
Okay.
Pick any algorithm and do this with it.
Okay.
Whatever, give your feature data into a support vector machine. Don't worry about what it is, but just say, I'm going to use that algorithm. Feed it into that algorithm, take 9 folds, train using support vector machine logistic regression. The one holdout, you're going to say, how did it predict on that data? I'm going to do it again. I'm going to do it again until I have 10 of those. Okay? So at the end, how many scores should I have for 10-fold cross-validation? 10. I should have 10 different accuracy scores for 10 different folds. Right? Again, this could be for any algorithm. It could be logistic regression. It could be neural network, support vector machine, decision tree. Any algorithm. In fact, you're going to do it for each algorithm that you choose to work with. And after a while, you get an intuition where maybe there's a family that you like to work with, 2 or 3, that you just kind of default to initially. Okay, so once we do that, we take our 10 scores from each fold. Fold 1 got 69%, 64, 73, and we'll get a mean. So over all the data, that algorithm is about 70% accurate.
So this one we are doing it so that we kind of average out. So why not do 20 times or 25 times rather than 10?
Well, you could, but again, you still have the data problem. If you do 25 times, you have to split your data between that, and that validation set gets smaller and smaller.
So there's no significance of 10.
10 again is the same. It's
just
standard.
common
Yes,
practice.
but again, your data problem is going to be different.
Sure.
But it's typical. You might want to go 5-fold,
Yeah.
7-fold.
Okay.
Yeah, but 10-fold is traditional.
Sure.
Yeah. So we got 70 for logistic regression. Okay? That's where Boxplot comes in. You do that for each algorithm. Now what a Boxplot does is called the little whisker up there at the very top, that line says that's the max value. The line at the bottom says that's the minimum value of those 10 scores. The line in the middle is the median value, not the average value. Who knows what the median is? Yeah, you're right, but I'm looking for something else in terms, you're right. He said it's the one in the middle, which is correct. But half the scores are above it, half the scores are below it is what I'm trying to get you to see. So if I had 68, 70, whatever I did, whatever score has half the scores above it and half the scores below it is the median, or also known as the 50th percentile. Okay, so a Boxplot is your friend when you're going to try to choose an algorithm. Okay, so right here I had 5 different algorithms, I ran them. You can see some of them are high, some of them like the naive Bayes was terrible. Its worst score was bad, 53 or so. But its best score was almost one of the best. But when I look at it, I like to first look kind of at the median and see where that median value is. And I'd like to look at the top value. So that leads me, in this case, which is a real case, I chose logistic regression, which is on the far left, and support vector machine. Those two look the best, most promising to me. So I would take those two, I might play around with them with their hyperparameters and all of that, but I would probably get rid of the other 3 and kind of focus on 1 or 2.
I think I missed that.
Yeah.
So what is the color-coded box and what are those dotted lines? And
Okay, those
what
are-
is the significance of the red line?
Excellent
Maybe if you
points.
can-
Excellent points. So
Yes,
you
well-
asked, I'm going to tell you. Okay.
Okay.
So this is called a Boxplot. And this Boxplot had those 10 values. Remember we did logistic regression. We got 10 values. Those 10 values are plotted in a Boxplot. So it's going to take whatever the least value is here, it's going to be that line at the bottom. Whatever the max value here is going to be the line at the top. And whatever value has half the values above it and below it is going to be the red line in the middle. So it gives you a good, where is the middle value, or the 50th percentile, and what is the max and minimum that that algorithm did. Now, because you asked, these are called, the color part is called the interquartile range. And what that means, if you look from that bottom line to the bottom of the box, it's the first quartile. From the bottom of the box to the median is the second quartile. From the median to the top of the box is the third. And from the top of the box to the max is the fourth quartile. And right in there between the second and third quartile is called the interquartile range. A lot of people will focus on that. And sometimes they'll say if anything is 1.5 times the interquartile range, it's an outlier. All this gets into statistics, but that's the point of that.
So essentially you're trying to get you choose the logistic regression, which is the first bar in this, and then you choose that because the red in the box is somewhere close to the middle.
You know, it's more art. You might choose something different, but just to me, in my mind, because it didn't have the highest score. In fact, there are 2 that were higher than it. But when I look at the median and on the whole, it looks promising to me. And so I went with that and support vector machine. I ended up using support vector machine ultimately, but I narrowed it down to those 2. Yes.
Why, in this case, would you say that negative phase is all over the place?
Well, I'm just saying its worst score is 50 something, its best score is 80 something.
No, I mean, but why the range?
I don't know what you mean, why the range?
Why
did it do that?
Why did some folds outperform other folds so drastically?
I can't tell you why. Whatever was unique in that fold, you know, sometimes because it's random. Like I said, maybe you got, maybe you learn over the whole data set, you got all the top people in that fold, and so it just didn't predict. I mean, there's a lot of reasons it's random. Yeah. I can't tell you that because my base is a good algorithm. It was simple, but yeah, those are good questions. Yeah, but because it's random, you can't tell what fold something got. You don't know why. Yeah.
So what made you choose support vector machine in the next step between that and logistic reduction? As you took that.
The simple. These are great questions. I love this, you guys. First of all, you guys know the difference between a parameter and a hyperparameter? Okay. You do?
No.
Okay. Parameter is learned from the data. Like if you're trying to predict a line, those coefficients, I won't get too much into it, but the point is that the parameters are learned from the data. You have nothing to do. For example, with weights for a neural network, that's learned from the data. You don't choose those. Okay, or linear regression. You don't choose what those coefficients are to draw that line. Hyperparameters are what you choose. You can choose how many layers in a neural network. You can choose what kind of kernel. I don't want to get too confused. You guys are using a support vector machine. You can choose, there's just different things that you can choose. For k nearest neighbor, you can say how many neighbors. For a k nearest neighbor algorithm, is it 3, is it 5? Again, we haven't gotten into algorithm, but the point is a hyperparameter is something you choose. So to answer your question is, after I narrowed it down to these 2, I went around and I played around with the hyperparameters and after doing that, support vector machine surpassed the other one. So that's a good question. At this point, you're really just narrowing it down. And once you could just say, if it's not that big a deal and your boss only wants, or if you have your own company, you only 75% is good, it may not matter. But if there's a significant difference for your boss between 75 and 76%, then you're going to take 2 or 3 and tweak them and squeeze everything out of it. So it just depends on the problem. So the point is, this is a narrowing down. That's all it is. And once you do that, you're going to play around with the hyperparameters and all of that. And then whatever one comes out best, that's the model you put in production or whatever. Okay.
So
Yes.
based on this plot, are we saying 72% is the max we can reach the accuracy there?
I'm sorry, say that one more time.
Are we saying that this is the accuracy that we can get at the max we are seeing?
Oh, no. That's just what it got on the training set. You still have to get it on the test set. You're still going to play around with the hyperparameters. This is just narrowing it down. What looks promising? That's all you're saying. Now you're going to go take it, play around with it, try to make it better. Maybe you'll get more data as well, clean your data, whatever you want to do. You might go back and do some back and forth, go back up to the top and come back down again and play around. And then once you feel good about it, you might be able to get up to 87%, 90%, depending on what the data set is. This just allows you to say, these look pretty good. I'm getting 70-something% right now with this. I feel good about that. These look like these models work well with my data. They may not work well with the next problem, but these models work well with the data I'm working on right now. The next step we do is we train on all of the training set. You guys get that? Why do we do that? Someone tell me, why do we do it? You guys know.
Use the maximum data.
Yeah, 3 for 3. Use the maximum data. Remember, we were holding out some data with the cross-fold validation. Now we got our model. Let's go back and train with that fold that we were holding out. Let's train on all of that training data. It's going to be more accurate. Okay? Now what do we do? Now we train on all the training data. We feel pretty good about our model. Now what do we do?
Test set.
Test set. It's the only time we go to the test set. Once we're good, we're done. We feel good about our model. It's performing well. We don't know how it's going to do on unseen data. Hopefully it's going to do well, but we feel good about it.
after you fold, then when you do with all the training data, do you do again some mean between those two?
No, you're done. Well, no, you're good with your model. It performed without that extra fold. So you're saying, I know it's going to do a little better with that extra fold in. Now I don't do anything else. I'm good. Now I can test it on that whole training set. It's already seen that set, but you can test on that training set to see how it does.
So you are not training. You are testing with all the training data.
No, I'm training the model again with all of the data now.
Together.
So that, yeah, all of it now. I'm not doing any more cross-fold. Cross-fold just allowed me to narrow down my model. Now that I've narrowed down my model, I'm going to train on all the data, and then now I'm going to look at my test set and see how I do on unseen data. In other words, how well it what? How well it what? I gave you guys a term.
When you say all the data, it's all the 70% of the data.
Yes, and we were holding some out, remember? And we're going to do that. We're training on all of the data, and going to the test data to do what? To generalize. Because it may do well on this, but maybe it's memorizing something that's peculiar about this data set, that it's just learned some peculiarities in it that doesn't show up. There's just some noise that it's learning, like we said earlier. We left those names in, and so it's predicting names well. But when you get different names, it's going to do terribly. So anyway, the point is we wanted to generalize on data we haven't seen. Because in the real world, when you put it in production, you have this model, and now you just have everything coming at you, and hopefully it can do well with data it's never seen.
Would you use something like that to eliminate features?
Can you do which eliminate?
The K-fold and this process of going through cross-validation to eliminate some of.
You wouldn't do it there. There's other ways that you could eliminate it, which I won't get into. There's other things that you can do. Once we've narrowed it down to 2 models, random forest and things has a way to prioritize the most important features that are contributing to it. So you can do that. But no, once you're at this phase, you're done with the data.
Okay.
You've cleaned it, you've put it in X, you've put it in Y, you're saying I'm good. I've done all I can do to the data right now. Okay?
So you wouldn't use something like that to feature elimination kind of?
No,
something
not cross-fold validation.
Okay.
Good question. And then, once we've done our test set and we like it, we do what?
The model is ready.
Run the whole model.
Run it all on all the data now. Training and test set. We're going to train that model again on all the data now. And now we're ready for production. We're ready for anything that's going to come our way. We feel good about it. We train it on all the data. So we train on the training set. So we can do cross-fold validate, holding a fold out. Then we bring that fold in and train again. Then we bring the test, and now we train on all of our data. Okay.
Maybe I'm having it, maybe it's a little too abstract for the training. What exactly concretely happening at the training? Are you giving some weights to each feature? And if so, if you're training at each step of the way, some of those weights must be changing, right?
They are changing. That's a good question. I intentionally not getting into that today. We're talking about the different algorithms, but when we get to talk about the different algorithms, we talk about all that, how you learn, how it's learning. But to answer your question, it's an excellent question, because what we call learning is those weights or coefficients changing in response to error. So if I make some prediction and I'm 63% or I have this large error, it's going to change the coefficients. And I get a little better, it's going to change. That's what we call learning. When those weights or coefficients are changing and changing and changing until we minimize our error.
So at the end of the day, it may not be the 0.72 we saw at the 10-fold, it may be 0.75 or
That's what, ideally, that's what you hope.
Okay.
Yeah, exactly. Excellent question.
So how do we determine that the test set itself is generalized well? Does it have to perform better than the training data?
It almost never will. It shouldn't, because you haven't seen it. You almost, if your test set is doing better than your training set, you're underfitting. Because you've seen the training set. It should do better than the test set, but they should be close. If they're too far away, then you're overfitting. They should be fairly close together. So if, let's say you got, you'd rather not have 90 on your training set and 60 on your test set. You'd rather have them both about 82 and 80 or something. You want them fairly close together, but almost always your test set will be a little poorer than your training because it's never seen it. It wasn't trained on that data. It should almost always do better on the data that it's seen.
If you have a specific target for accuracy, let's say 90%, and our model is, say, coming up with 85%, what do we do to improve it?
I love that. What would you guys do?
Okay, different algorithm.
That's one thing. What else would you guys do?
Get more data.
Thank you. Get more data.
Get more data.
Get more, I mean, there's a lot of other things you can do. You can tweak, you can do grid search, you can do hyperparameters, but the surest thing are two things. I'm gonna talk about one in a minute. One is get more data, and two is feature engineering. Create better features. Those are two things you
We can choose what.
You know, you're gonna create it. Okay, and I'll talk about that, but feature engineering and creating and getting more data are the two best things that you can do to improve your model. And you don't always have control over getting more data. Okay. Okay, let me give you guys an example. This is a product I've worked on. How many of you have Spotify, iTunes Music? Spotify? Yeah, Spotify. Anyone iTunes Music? No one. That's a shame. Wow. I love Apple, but I have Spotify because they got me early, and it's hard to switch. We have all this music, but anyway, the point is, we talked about this. I want to give you in kind of a general sense. Now, this was my problem. So I want to give you guys the sense, kind of a walk through how your heads might be working when you're doing your problem. Because a lot of good problems come from your life, what you love, what annoys you. And so I love music. I love Spotify, probably Spotify first then Netflix. If I just didn't have anything, couldn't eat, I probably still would play for Spotify. I love it. I love it when I'm coding, I just love music. So the point is, most of you have Spotify, and some of you may not know, Spotify has something called Discovery Weekly. And they give you 30 songs every Monday that they think you're gonna like. And from someone who's in machine learning, it is magic. It's incredible. When I first started pulling in my microphone, 1 or 2 songs, I probably pulled half the songs and put them in a playlist. It gets how my head hears music, it gets me, I don't know how it does it. I'm so bad inside now, but it's incredible. So what I said, and sometimes in this, and sometimes for songs I don't like. And so the question I came up with, remember the first thing we talked about, what question are you gonna ask your data? The question I ask my data is, can I predict for a specific song, not globally, but very specific, can I predict when Spotify recommends a song to me, can I predict which songs I would like? And which songs I won't like. That's a problem I wanted to solve. That was for me. It's not out anywhere. And so what I did is I got my data. As I showed you earlier, I used Spotify's API. Okay, they're called acoustic feature, but it's an API that's available. Most public sites like this have an API where you can get to data, especially if it's your own data. So what I did is I took songs. Every time they gave me a song, I had to love it instantly. If I loved it instantly, I put in the like, so to really get what I like. And if it's a song I never listen to again, I put it in rejected. Anything in between, where it's okay, I might play it a little bit, I didn't put it in either category. So I wanted to distinctly know what I love and what I don't like. And I put those in 2 playlists, so that's my training data. So now I got my data. I have my question, I got my data. Okay? So
How many songs?
if you look there, and the like was 334 liked and 331 rejected, was the training set. It was split in the test training, split, but that was my data set there. Here's some of the features, over 600 different features. This is in Spotify's API, but this is just some of them that you can see. Okay. Next, I explored my data. I visualized it. I want to see what is what. I mean, there's some reason I like a song. I have no idea. We can't verbalize why we like a song or why we like a food. Sometimes you may taste a food and say, how can anyone eat that? It's the same thing with a song. How does someone like that song? I can't tell you why, but I want to visualize and say, what am I liking and what is it? So here I looked at popularity, okay? Because Spotify largely doesn't recommend songs on popularity. They have a taste profile on each person. They get a sense of what you're listening to, what you like. They do factor in popularity a little bit, but a lot of it can be 0. So as you see, the green is what I liked, the red is what I didn't like. Okay, so you can see a lot of my green is down in the 0 area. I mean, no popularity. Clearly I'm not listening to the top 100 because I'm nowhere down there with the hundreds and the 90. I don't listen to any of that music. But, let me clarify one thing. The music is called chill. I don't know if you guys know what that is. Kind of R&B, hip hop, Cirque du Soleil. Anyone familiar with Cirque du Soleil? I intentionally chose music that didn't have words. Because words can make you like a song. And I'm not factoring that in. I'm not doing anything on the words, on the lyrics. So I intentionally chose songs, if there was any vocals would be in the background humming or something like that. So I was very narrow on what I chose to do this. Okay, and at the bottom is the histogram. On the top is a density plot, just kind of a smooth histogram so I can see them overlap. Okay? Then here I looked at tempo, and there's definitely some signal there for tempo. I don't know why, maybe about 125 beats per minute. There was something there, I don't know why or what, but that's what I got. So I started thinking about that in terms of maybe getting some signal, looking at something there. So this is feature engineering. As I said, when you're not doing well, get more data or do feature engineering. So what I did is I looked at some of the genres, and you'd be amazed how many genres there are, subgenres that I wouldn't even know. You think you're listening to R&B or something else, and you're not. You're listening to all these. You can see the ellipses at the end. It goes on and on and on for some of these subgenres. So I looked at some subgenres first of all. Then I said, let me look at the top 30 of the songs I like, and the top 30 and the 30 of the songs that I rejected. And they overlap a little bit, but Vapor Twitch, whatever that is, I don't even know what Vapor Twitch is, but it was my #1, and it's not at all on the rejected list. And the dubstep was not at all on the liked list. So there's some signal there, so I'm doing some feature engineering. Now I'm saying there's something to those subgenres. So again, I visualized the histogram of my top, the frequency of my top 30 of the liked. Okay, and I said, okay, well, let me see what that same frequency of those same features, but for the songs I didn't like. So I can see there's a big difference there. So what I did, I created a feature that said, it was called in liked genre. So I knew that if a new song came in that had one of these, there's a better likelihood, it gives me some signals, a better likelihood, perhaps I would like it. Okay, so again, that's what feature engineering is. So I created that feature. Real quick, I'm not going to talk about those, I just want to show you, because it's a real project I did. It says that when I said I wouldn't like a song, I was right 89% of the time. And it said when I said I would like a song, I was right 73% of the time. And again, that's up to you how important those numbers are. Is it more important to keep bad songs out or to pull good songs in? That's a choice that a person has to make. Okay? Okay, let's move on here. That was largely about data science and kind of give you guys a sense as maybe how you're thinking, how you're kind of moving through a project. Let me talk a little bit. I want to differentiate for you guys machine learning and artificial intelligence. Roger, how are we doing on time? You okay?
If you want to take a break with that.
You want to take a break with that? It's a good time. Yeah, now's a good time.
Will we get into some sort of, you're going to do actual code and demo?
I'll do that.